Okay, this is actually problem 5. So we kind of skipped ahead a little bit to problem number 5. So notice in problem number 5, let me go ahead and change pen colors here. Number 5. Essentially, there are two events that they're asking about. They're asking about that the person has at least one credit card, and also that the person's male. So these are two separate events, and we're looking for the and, or intersection of the two. Okay, so basically we want, so let's call the events A equals at least one credit card, and we'll call the event M is male. Okay, we could use B for male, but like A and B, but I'll just stick with M. It's easier to remember. Okay, so A, at least one card, M is male. So they want the probability of A and M. Okay, now, can I just take the probability of A and multiply it times the probability of M? Can I get the probability of M? What would be the probability of M? Probability of M is going to be, if you remember your probability definitions, it's going to be the number of outcomes in the event M, and the event M just means that person's male, divided by the number of outcomes in the whole sample space. Okay, and the sample space is everybody, the set of all outcomes. Number of outcomes in the event male is going to be 9 plus 12 is 21, plus 5 is 26. Number of outcomes in the whole sample space is going to be, well, let's see, I've got the 21, I've got the 26 males, and then let's see, plus another 20 is what? 46, then 10 is 56, plus another 7, 63. 63 people total, and if I do that on my calculator, 26 over 63, I'm getting, let's see, about 4.4127 approximately. Okay, now what about the probability of at least one card? At least one card means, at least means that or more. So that means these two columns right here. These guys and these guys going down the columns. One card or two or more cards to give you one or more. Okay, so how many people total in all these two columns? Let's see, I've got 30 and 12 is 42, 47 total, right? So this is going to be, so the probability of A, again, there's 47 ways to get event A, and there's 63 ways to get any outcome. Okay, and so if I divide that, I get what? So 47 over 63, I'm getting 0.7460. Now, the next question is, can I just multiply these? Can I take the 0.7460 times the 0.4127 to get the probability of A and M? And the answer is only if they're independent. Is the number of credit cards that you own and your gender, is that independent? Maybe, maybe not. We don't know. Okay, so I cannot assume that I can just multiply them. Okay, we cannot assume that they can just be multiplied. So we can't assume that the probability of at least one card and being male is equal to the probability of at least one card times the probability of being male. We don't know, so we cannot assume that. Okay, we don't know. It is only if they're independent. And we don't know if they are. We can get it, so is there another way around this? And the answer is yes. Since we have the actual sort of what's called the raw data, we have the count of each person's, like all the different males and how many cards they had, and all the different females and how many cards they had, we can get the probability directly. The probability of A and M, I can just do the direct method. We can just do a direct count. We can just count how many people are in the event A and M at the same time. So where's the event A and M at the same time? You'd have to be in the A column, which is here. Those two columns together make the A, and this is the M row. So how am I in the M row and the A column at the same time? And the answer is these two guys right here. Okay, those two guys are in the male row and the one or two or more cards. So the direct count would be number of ways or number of outcomes to get A and M at the same time. That's an and, sorry about that. Divided by number of ways to get anything. for any outcome. In other words, this whole sample space. And we saw that that's going to be 17, and there's 63 in the whole sample space. So if I divide 17 by 63, what do I get? So 17 over 63 is 0.2698. Okay? Or if in terms of, since they want us to round to 2 decimal places, that would be approximately 0.27, right? Which is what they're going to get. Now the question is, I did the direct count. Why? Because I could not assume that the two events, the event at least one card and the event mail, are independent. Now, in retrospect, since I have the numbers, can I check? What if I did multiply these? What if I multiplied them? I'm just kind of curious what would happen. So if I take these guys and multiply them, if I do 0.7460 times 0.4127, I get, I'm just seeing what I get, okay? And when I do that, so 0.7460 times 0.4127, I'm getting 0.3079. So if I assumed that the two events were independent, roughly about 31% of the people should be male and have at least one card, if they were independent. Am I getting 31%? No, I'm getting about 27%. I'm getting a lower number. That means that they're not independent. That means they do influence each other, and in fact, they're making each other less likely. If they were totally independent, I would expect 31% of the people to be both male and have one or more cards. But I'm getting 27%. That means if I know someone's male, it makes it less likely they're going to have one or more cards. Or vice versa, if they have one or more cards, it makes it less likely they're going to be male. Because I'm getting 27% have both characteristics at the same time, whereas I would have expected 31% if they were independent. Okay? So this is going a little bit above and beyond the question, but it's kind of interesting. Okay? So they're not independent. I cannot just multiply them and get the answer to the question. And in fact, we've showed that they make each of these two events makes the other one a little bit less likely to occur. Okay? So they're dependent on each other kind of in a negative way. They're kind of reducing the other probability, which is interesting. Okay? All right, so let's go on to the next one. Okay, so this is problem number 6. And let's see, so this is problem number 6 here. So they want to know what's the probability that the person has no credit cards. So let's give that a name. Well, I guess we'll call this N, I guess, for no credit cards. And male, we'll call this M for male. Okay, so we want to know the probability of N or M. Okay, now, how do we get that? Well, or is essentially a sum. You add. And you multiply as long as they're independent. Okay? If they're not independent, you can't multiply for and. So probability of, just to review, like one event and another, essentially that's a multiplication problem unless they're not independent. Okay? So if they're independent, you can do this. You can do probability of A times probability of B. Okay? If they're not independent, or if we can't assume they're independent, then it's more complicated. Okay, and we'll get to that in the next section. Okay, when we get into a little more complicated scenarios. Okay, but we can always do a direct count, like we did last time. What do I mean by direct count? Just count how many people had both characteristics at the same time and divide by the total number of people. Okay, you can always count directly. The question is, can you compute the and based on the two individual events? And the answer is easy to do if they're independent, not so easy if they're not independent. Okay? What about or? Or is a whole different ballgame. Or is typically a sum. Okay? So just to review, if you go back through the material for the section, probability of one event or another, let's just call them A or B, is equal to the probability of A plus the probability of B Just like that, straight like that, if they are what's called mutually exclusive. Mutually exclusive means they don't occur at the same time. Okay? You can't have, if you have one, you cannot have the other. So like, for instance, wearing sneakers, not wearing sneakers. Drink coffee, don't drink coffee, that sort of thing. Those are mutually exclusive events. If one's happening like over 6 feet, under 6 feet, that sort of thing. Those are mutually exclusive events. Okay? If they're mutually exclusive, you can just add the probabilities to get the or. What if they're not mutually exclusive? Well, this is something we've already studied. It's in the section. It's probability of the first guy plus the probability of the second guy minus the probability of the overlap, the intersection. This is the so-called overlap. This is both at the same time. Okay, because the A and B, the overlap gets double counted. It gets counted in the A's and it gets counted in the B's. So it's getting double counted, so that we have to subtract it off. If they're mutually exclusive, there is no overlap. Because if mutually exclusive means if you have one, you cannot have the other, so you can't have an overlap. So if they're mutually exclusive, there's no overlap. The overlap is gone. That's why this works if they're mutually exclusive. Okay? So mutually exclusive means one of them excludes the other, makes it impossible to have the other, and that allows you to add to get the or. You can add to get the or if they're mutually exclusive. Okay? If they're not mutually exclusive, then to get the or, you have to use the slightly more complicated formulation. Okay? If they're independent, you can multiply to get the and. If they're not independent, it's a little more complicated, and at this point, we're just going to use a direct count of all the A's and B's together to get the and, but there's some other methods we could use later on. Okay? Now, how do we solve this problem here? Can we assume that these two events, no credit cards and mail, are mutually exclusive? Well, think about it like this. If you're male, does that mean you cannot have any credit cards? Or does that mean you have to have credit cards? Does being male exclude something about the credit cards? No. Okay? So they're not mutually exclusive. Another way to tell is I can look on the table. Can you have both at the same time? Can you have no credit cards and be male at the same time? And the answer is yes, you can. That's the overlap. That's my overlap of the two events. That means there is an overlap, which means they're not mutually exclusive. Okay? So I can go ahead and compute the probability of the or using this basic formula, and I'll let you guys finish that up. Okay? Probability of event A, so in this case we're going to do, so probability of N or M should be probability of what? N plus probability of M minus the double count. You want to minus the N and M at the same time, the overlap, because those got double counted. They get counted as part of the N's, the no credit card people. They also get counted because they're part of the male group, and so they get counted twice. And we subtract off one of those counts. Okay, so you should be able to get these two numbers from the data itself. For example, the probability of no credit cards is going to be what? There's going to be, how many people have no credit cards? 10 ways for that to happen out of, what's the total? Looks like, let's see, 10 and 20 is 30, 35, 40, 48, 55. Looks like 55, 10 out of 55. Okay? Plus, and I'll let you guys finish this up. Okay? You should be able to finish that up pretty easily. Cool. Okay, so this is number 7. For number 7, they're asking for a not, the opposite of something. So we're being asked for the probability that the person did not have one credit card. Now there's two ways to do that. Not means complement. Not means opposite or complement of an event. Okay. So if I let A equal one credit card, then A's complement would be not one card. Now, there is the complement rule. Remember, the probability of the complement of an event is 100% or 1 in decimal world minus the probability of the event itself. So it's easy to get the probability of a complement if you know the probability of the original event. You could just do 1 minus it. Okay? That's the easiest way to get the probability of a complement, okay, of an opposite. The other way is you could just, so let's go ahead and do that first. So what's my event here? 1 card, right? So do I know the probability of 1 card? So let's go ahead and get that. What's the probability of 1 card? In this case, we'll call this event A. Probability of 1 card is, well, there's 22 outcomes in the event. How many outcomes in the whole sample space? 20, 30, 39, 45, 57, looks like 63. Okay, so that's the probability of event A. Okay, so if I do that on my calculator, I'll get, let's see, 22 over 63. I'm getting about 0.35. Okay, now what's the probability of A complement? Probability of not, so this is 1 card. So the probability of not 1 card opposite, so not 1 card. That's supposed to say not. Sorry, it looks like net, but it's not 1 card. Okay, is going to be 1 minus the probability of 1 card. Okay, which is going to be 1 minus the 0.35, which is about what? 0.65, right? Now, that's using the complement rule. Could I have gotten this directly? And the answer is yes. In this case, the complement of the event is pretty simple. It's a pretty simple scenario, so it's pretty easy to count the complement directly. So I could just do a direct count of the complement. All these 4 sets of outcomes would be in the complement. This would be in A's complement. Okay, so I can just directly get probability of A complement just thinking of that as an event on its own. Okay, that's going to be the number of ways you can have A complement, which is going to be what? 9 and 6 is 15, 35, 41. Okay, out of a possible 63 people. What's 41 out of 63? I'm getting 0.65, right? Which makes sense. That's what we figured. Okay, 0.65. So I can directly compute A complement as an event on its own, or I could just do probability of A and do the opposite, or the subtraction from 1. It's good to know that method, because if you, let's say that I had like 50 different kinds of outcomes here, like 50 different kinds of credit card scenarios, and I wanted the complement of one of them, then I'd have to like add up all the 50 others if I want to do it the direct way. But if I use the complement rule, I could just get the probability of the one scenario I'm looking for, the one event I'm looking for, and then do 1 minus that to get the complement. So the complement rule is super helpful, especially if you have lots of events going on. Okay, so this one should be pretty easy. All right, let's go on. Okay, this is actually problem number 9. Let me go ahead and bring up the sketch pad. So on problem number 9, let's just remember our basic rules here. For the probability, they're giving us the or, they want the and. Okay, what's the formula for or? It's the probability of the first guy plus, or is always a plus, probability of the second guy minus the overlap. So normally we would know the overlap, we would know the and we would know the individual probabilities of each event by itself, and we would compute the or. But in this particular case, they want us to kind of work backwards with this a little bit, which is okay. They're giving us the or. They're telling us that this is 0.85. Okay, they're telling us that this guy is 0.45. They're telling us that guy is 0.65. So if you add up 45 and 65, what do you get? You get 1.1. Well, first of all, any probability over 100% is impossible. So if your probability ends up more than 1.0, you made a mistake. You can't have more than 100%. But the issue is A and B are not mutually exclusive events. There's an overlap to them. Okay, the question is how big is the overlap? So this guy here is actually the overlap between the two events. They're both at the same time. That's the overlap. How big is the overlap? Well, we don't know. But I know it has to be subtracted from the sum of the individual probabilities, because that's how overlaps work. The probability of A or B occurring, you have to add the A plus the B and subtract off the double counted people. Okay? And we can solve for the A and B this way. All right, this is kind of a neat little way to solve for A and B if you know the individual probabilities and you know the probability of one or the other, okay, which they're giving us here. All right, so this should be pretty straightforward for you guys at this point. All right, let's see, that was number 9. I guess let's take a look at number 10. Okay, this is problem 10, and we actually don't even need the sketch pad, because think about, what does mutually exclusive mean? Mutually exclusive means no overlap, right? That if one occurs, the other one cannot occur. What's an example of mutually exclusive? Someone's over 6 feet versus someone's under 6 feet. Like if event A is you're over 6 feet and event B is you're under 6 feet, then they can't both occur at the same time. Okay? That's an example of mutually exclusive. So they're asking you for the probability of A and B at the same time. So if they're mutually exclusive, what does that mean about the probability of both occurring at the same time? That should be a pretty simple computation or deduction for you. All right? So let's move on. Okay, so this is, I guess, number 11. Let me go ahead and bring up the sketch pad real quick. So we're on number 11, if you like problem numbers. Okay, if you don't like problem numbers, well, we're still on number 11. Okay, all right. So now they're giving us the probability of each event separately, and they want to know about the or, one or the other. So what's the basic equation for the or? Probability of the first guy plus, or means you add. But you double count, so you have to subtract off the double counted people. That's your double counted people right there. That's your overlap. The overlap gets subtracted off. Okay? Now, they're giving us what? They're giving us some stuff. They're giving us probability of A. They're saying, yo, that's 0.69. Okay? B, they're saying, yo, that's 0.11. Okay? So I can add those. They want to know the probability of A or B, right? That's what my question is. So that means I have to subtract off the probability of A and B. So how do I get that? Well, the clue is they're mutually exclusive. So if they're mutually exclusive, what does that tell you about A and B at the same time? Okay? And once you know that, you should be able to insert that result here and figure out your answer. Okay? All right, cool. Let's move on. Okay, this is problem number 14. And so I've actually pulled up a picture of the dice just because I know it's a dice problem. So let's go ahead and analyze this. So number 14, first of all, let's put the number down. So we're on problem number 14. And so the probability of showing a 2 on the first roll, that would be one event. Okay, we'll call that event A. And then an odd number on the second roll, we'll call that event B. And it's an and, right? And means what? Well, can we multiply? How do we get this? Well, let's see. First of all, where can we, where is the 2 on the first roll? So the red die is the first roll, the green die is the second roll. So if I get a 2 on the first roll, the only way for that to happen, the first roll is the red die. So a 2 on the first roll would be all of these outcomes right here. Would be a 2 on the first roll. Roll a 2, then a 1, or roll a 2, then a 2, or a 2, then a 3, 2, then a 4, 2, then a 5, or 2, then a 6. All of these would be 2 on the first roll. So that's my event A, is this collection of outcomes. There's 6 outcomes in event A. Each pair of die, each pair of pictures is one outcome, okay? Because we're rolling a pair of die. So this is one outcome, another outcome. There's 36 possible combinations. So there's 36 possible outcomes here. Now, what about an odd number on the second roll? So let's kind of switch colors here. Odd number on second roll would be, well, let's see, second roll is the green roll. That's going to be an odd number on the second roll. That means you're going to have this column is an odd number on the second roll because they're all 1s. This column is an odd number on the second roll because they're all 3s. This column's all 5s. Okay, so we want the probability of both together. Well, can I count that directly? The answer is yes, I can. Direct and means the overlap. Okay, so I have enough information. Where's my overlap? Where's my overlapping locations? Right here is an overlap. Right, so in other words, this is, I should have notated this. This is event B, right? All of this is event B. B is here and here and here is event B. B is an odd number on the second roll. All of these 6 outcomes, these 6 outcomes, and these 6 outcomes all have an odd number on the second roll. Okay, so B is existing in 3 different columns here. But anyway, let's go back to counting the overlap, the and. And means overlap, both at the same time. So that means you have to be in A and you have to be in B at the same time. So these 3 outcomes are in both at the same time. So we already have our answer. Okay, probability, we can do this problem several ways, but the most direct way to do this is probability of A and B is simply the number of ways it can happen, number of ways or outcomes for A and B. Think of A and B as sort of its own like little event divided by number of ways or outcomes for the whole sample space. I'm just going to write SS for sample space, if that's okay. So now that's going to equal, well, how many outcomes are in the event A and B? Like we said, 1, 2, 3. Okay, there's 3 ways for A and B to happen out of 36. Okay, 3 out of 36. Or you could reduce that to 1/12, or if you like decimals, that would be 0.0833, if you like decimals. Right? But if you don't like decimals, well, it's still 0.0833. You're just not crazy about it, right? Okay. Or 0.08 to 2 decimal places. Done. Problem's over. Now, but can we learn a little bit more from the problem? And the answer is yeah, we can practice some of our other formulas. What's the relationship between the and the or? Well, the basic relationship there we should know is probability of A or B is the prob of A plus the prob of B. See, I'm using we're pro now, so we can just say prob, saying instead of probability, right? P of A plus P of B minus the overlap. And the overlap is what we're looking for, right? So if I know the other 3 things, I can just solve for the overlap that way. Now, I don't need to use this formula because I have the direct count. This is the direct count method. But you can't always count on that. Sometimes you don't have a listing of all the sample space elements. In this case, I have an exact listing of all the sample space elements because it's a well-understood sample space. It's just rolling 2 die, right? But sometimes I don't. Sometimes I would have to count on this. This is sometimes called the indirect method, using these other components to figure out the A and the B. Okay, and I would have to use this indirect method if I don't have the exact listing of everything in the sample space. So for example, do I know probability of A? Well, probability of A is 6 out of 36. How come? Because there's 6 elements in that row out of 36 total. There's 6 outcomes in this A row divided by 36 possible total outcomes. What about the probability of B? I've got 6, 12, I've got 18 of them out of 36. Okay, that says 18. Sorry about that. I guess let me change colors here a little bit. I guess this color's not showing up good at the bottom. I can try a brown here. So this would be 6 out of 36. This would be 18 out of 36. Okay, we're looking for this guy. But do I know the or? And the answer is or is if you're in one or the other or both. So basically if you're in any of this stuff, I'll just kind of shade it in. This, or this. If you're in any of the shaded regions, you're in the or. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So this would be 21 out of 36. and this is x. We don't know it, right? This is what we're trying to solve for. So this is the indirect method. So can I find it? Well, I could convert these to decimals if I want. So I've got 21 out of 36 is equal to 6 out of 36 plus 18 out of 36 minus x. So 21 out of 36. Now, by the way, what is 636 plus, whoops, sorry about that. What is 636 plus 1836? Isn't that, can I just, since I have a common denominator, can I just add them up? 18 and 6 is what? 24, right? So I have 21 out of 36 is equal to 24 out of 36 minus x. Can you figure out what x is? What do you have to subtract from 24 to make it 21? 336, right? So I can just work in fraction land and get the answer, 336, which is what we got here. Okay, now obviously the direct count method is great. The direct count method is direct. You can just do it directly. Okay, so if you have a listing of all your sample space components, all your elements of your sample space, a full description, just do the direct count method. It's fast, it's easy, you won't make a mistake. You have to use these combination rules if you don't have a listing of everything. You only have partial information, then you have to rely on these other rules. Okay, so I would not necessarily do this method. I would use this method right here, the direct count. I'm just showing you that the other method does still work. Okay, all right, cool. Okay, this is problem number 14. And so let me go ahead and bring up the pen so we can kind of write down some stuff. I brought up the dice image again because it's a dice problem. So just in general, so this is number 14. Or. Okay, so we'll call this 5 on the first roll. We'll call that A. Odd number, B. What's the probability of A or B? Prob of the first plus, or is plus, but you have to minus the intersection. Right? That's an and. All right? That's the intersection or overlap. Now, the next issue is, do I have enough information? They want me to find A or B, right? So they want this guy. Okay, do I know probability of A? What is A? A is a 5 on the first roll. So which of these events would be a 5 on the first roll? I'm sorry, which of these outcomes would be in the event? Which of these outcomes, each pair of dice is one outcome. Okay, so I have a 5 on the first roll. Well, the red die is the first roll, so this event is has a 5 in the first roll. So does this one, so does this one, so does this one. In fact, there are 6 events where you've got a 5 on the first roll. So that's my event A. All 6 of those outcomes are in the event A. Okay, what about the event B? Odd number on the second roll. Okay, odd number on the second roll. That means the second roll would have to be here. So these guys would all have an odd number on the second roll. These guys all have an odd number on the second roll because they'll have 3s on the second roll. And these guys all have 5s on the second roll. Maybe green wasn't the best color to pick, but anyway, let me try a different color there. Sorry about that. I guess we'll try a little lavender. I don't know. Now, just mucking it up a little bit. I guess you can tell I'm not exactly a good interior decorator here. All right, my color choices are a little suspect. But anyway, so this is all event B. Event B is kind of in all 3 columns. This is event A. I guess I'll kind of do a single kind of oval for it there. That's all event A. And so now, do I have enough information? Do we have what we need? Do we have, for example, do we have the probability of A? Yes, we do. Do we have the probability of B? Yes, we do. Do we have the probability of the overlap? Yes, we do. So we can just use the formula to compute A or B. Okay? The other way we can compute A or B is, since we have a description of the sample space, we can actually count A or B directly. How do you end up in A or B? That means if you're in A or if you're in B or both, you're in what's called the compound event. This is what's called a compound event. It's 2 events joined together by an or. Okay? Anytime you join events together with an or an and, that's called a compound event. So this compound event of A or B, I can just count that directly. If you're in A or if you're in B, you're in the compound event. That means if you have a 5 on the first roll, or if you have an odd number on your second roll, you're in the event. I can just count that directly. You should practice counting that directly. Make sure you get the same result as using the formula. Okay? All right, cool. Let's take a look at, I guess, maybe one more problem. All right, so our last problem here, I think this is number 16. So let's work on this a little bit. There we go. Computer's a little slow. Been a long week for this computer. All right, so again, this is number 16. So what do? Well, we're asked for what? Male or C student. Okay, so we'll let M equal male. We can let C equal C student. It's safe to do that. Usually we reserve C to mean the complement of an event, but we're not dealing with any complements here, so we can just use C for the fact that it's a C student. Okay? So we want the probability of male or C. Now, according to the basic formula, what is that? That's probability being male plus the probability being a C student minus the overlap. Do we have all those components? Yes, we do. I'll leave that up to you, but the answer is yes, we got it, yes, we got it, and yes, we got it. Okay, so we can do this using the formula. We could also do this using direct count. To do a direct count, just go through and say, okay, if you're in the event M, you're in the compound event, M or C. If you're in C, you're in the compound event. If this was an and, to be in the and, this is also a compound event, but it's an and. To be an and, you have to be in both at the same time. So how about M and C? Who's in M and C at the same time? These guys. That's it. Okay? So that means you have to be in both at the same time. Right? So this is obviously going to be 13 over whatever the total number is in the sample space. I'll let you guys figure that out. Okay? So for or, you can be in either one. Okay? So I could do this as a direct count, so I can use the formula. I have all the parts I need, or I can use direct count and just count my event directly, my compound event, M or C. All right, just count it directly. Both should be the same result, and you should be able to do both methods. The reason I can do the direct count is because they're giving me a listing of like who did what. Okay, like all the males and how they scored, and then all the females and how they scored, right, or what their grade is, whatever. So because I have that information, I have a kind of basically a description of everything going on in the sample space in terms of these events, so I can do direct count method or formula. Sometimes you can't. Direct count's great if you can do it. But if you can't, you have to rely on the formula. So you want to be able to do both. Okay? Just practice doing both and just realize that direct count's not always available to you. Sometimes, like suppose they just told you outright, hey, probability of male is this, probability of a C student is that, and the probability of both together is this. You can't, and they don't give you the table. Then you can't do direct count. You'd have to use the formula. So you got to be able to use the formula. You can't always rely on direct count. But you also want to know how to do direct count for the cases where you do have a full table or a full listing of the sample space. Okay? So this one's actually pretty easy once you know the system. All right, cool.